Hey Bob, I've been going through a big stack of quantum computing papers from March 2026, and honestly, there's a lot to unpack. Where would you even start with a month like this?
It's a rich month, no question. If I had to pick a single headline result, it would be the paper by Cain, King, and colleagues titled Shor's algorithm is possible with as few as 10,000 reconfigurable atomic qubits. For years, the conventional wisdom was that breaking RSA 2048 would require millions of physical qubits. This work slashes that estimate by roughly 2 orders of magnitude by combining high-rate quantum error correcting codes, efficient logical instruction sets, and clever circuit design on a neutral atom platform. It's a genuine paradigm shift in how we think about the timeline to cryptographically relevant quantum computation.
That's striking. So, what specifically makes neutral atoms so well suited here compared to, say, superconducting qubits?
The key is reconfigurability. Neutral atom arrays can physically shuttle atoms around, which means you can implement long-range connectivity and parallel operations that are very expensive in fixed topology architectures. Cain et al. Leverage this to exploit high-rate codes that encode more logical qubits per physical qubit than the surface code. And they show that with around 26,000 physical qubits, you could crack elliptic curve P256 discrete logarithms in just a few days. RSA 2048 takes longer, maybe 1 to 2 orders of magnitude more time, but it's still within reach. Recent experiments have already demonstrated fault-tolerant operations below threshold and arrays of over 6,000 coherent qubits. So the engineering path, while challenging, looks credible.
Speaking of discrete logarithms, I also saw a paper by Xu, Chu, Xiao, and colleagues on a distributed quantum discrete logarithm algorithm. How does that relate?
It's a complementary angle. So the paper titled Distributed Quantum Discrete Logarithm Algorithm tackles the same cryptographic problem, but from the perspective of hardware limitations today, specifically that no single quantum processor is large enough. Their approach breaks the problem into set intersection subproblems that can be solved on smaller registers, and remarkably, they require no quantum communication between nodes. So rather than waiting for a single giant machine, you could potentially distribute the computation across multiple smaller devices. It reduces register size and can even improve success probability compared to Shor's original algorithm.
That naturally raises the question of what cryptographers should be doing right now. There were several papers on post-quantum cryptography and related threats. What stood out to you?
3 things stood out. First, the paper Post-Quantum Cryptography from Quantum Stabilizer Decoding by Liu, Paremba, Kwek, and Ramkumar proposes a genuinely new hardness assumption decoding random quantum stabilizer codes and shows it implies public key encryption and oblivious transfer with efficiency comparable to state-of-the-art LPN-based schemes. This is important because post-quantum security currently rests on very few assumptions, so diversifying that foundation matters. Second, on the practical feasibility of harvest now, decrypt later attacks by Blanco Romero and colleagues reframes the HNDL threat as an economics problem, quantifying adversary costs across TLS and SSH. Their key finding is that data archiving is essentially free for adversaries, so the real defensive levers are aggressive rekeying and larger key exchange parameters, which multiply the quantum computation required to decrypt. Third, the spectral methods paper by Bellis, Bowles, Gupta, Peters, and Schold, Spectral Methods, Crucial for Machine Learning, Natural for Quantum Computers, argues that quantum computers are naturally suited to manipulating Fourier spectra of machine learning models, which is a more forward-looking framing of quantum advantage.
The stabilizer decoding paper sounds fascinating. Is the hardness assumption really distinct from LPN, or could someone reduce one to the other?
That's exactly the right question, and Liu et al. Address it head-on. They provide substantial evidence that quantum stabilizer decoding does not reduce to LPN, which would make it a genuinely new post-quantum assumption. The technical reason is that stabilizer codes carry symplectic algebraic structure that LPN lacks. They develop new scrambling techniques to handle this structure in their security proofs. So if LPN were ever broken, stabilizer decoding-based cryptography would likely remain secure. That's the diversification benefit.
Let's shift to fault tolerance because there were a lot of papers there. The result from Perlin, he, and colleagues on actually executing error-corrected algorithms end-to-end seemed like a milestone.
Absolutely. Fault-tolerant execution of error-corrected quantum algorithms is one of the most practically significant papers of the month. They ran QAOA and the HHL algorithm on Quantinuum's H2 and Helios trapped ion processors using the Steen or 713 code, fully fault-tolerant, no unencoded shortcuts. For QAOA on up to 8 logical qubits, they achieve performance comparable to unencoded circuits, and for 12 logical qubits encoded in 97 physical qubits with over 2,000 2-qubit gates, they still observe better than random performance. The logical T-gate infidelity is around 2.6 times 10 to the minus 3. This is the first demonstration of end-to-end FT algorithm execution using only fault-tolerant components, which closes a major gap between proof of principle QEC experiments and actually running algorithms.
How does that connect to the star architecture papers from Toshio Kanasugi and colleagues? There seemed to be a whole ecosystem of early fault-tolerant ideas there.
Great connection. The paper Star Magic Mutation by Toshio Kanasugi, Fujisaki, and colleagues introduces a protocol that combines transversal multi-rotation with magic state cultivation to implement logical rotation gates with dramatically better error scaling, roughly quadratic improvement over the previous state-of-the-art for small angle rotations. For rotation angles below about 10 to the minus 5, they claim a 2 order of magnitude reduction in both execution time and error rate. Their companion paper, Enabling Chemically Accurate Quantum Phase Estimation in the Early Fault-Tolerant Regime by Kanasugi, Toshio, Maruyama, and Oshima, applies this star architecture to quantum chemistry, showing that ground state energy estimation for active spaces of 20 to 50 spatial orbitals, well beyond classical full CI, is achievable with around 100,000 physical qubits and runtimes of days to weeks. Together, these papers define a credible near-term path to useful quantum chemistry.
On the topic of quantum chemistry, there was also a provocative paper by Legeza, Menzer, Werner, and a large team arguing that classical methods are still very competitive. What's the story there?
The paper Hunting for Quantum Advantage in Electronic Structure Calculations is a highly non-trivial task, is a reality check. They push classical DMRG, density matrix renormalization group, to unprecedented scales using NVIDIA Blackwell GPUs, achieving high accuracy ground state energies for the FE4S4 cluster in a CAS 54036 space, and even tackling active spaces up to 89 electrons in 102 orbitals. These are exactly the kinds of strongly correlated systems that quantum computers are supposed to excel at. Their point is that before claiming quantum advantage, you need to benchmark against the best classical methods fully exploiting modern GPU hardware. And those methods are still advancing rapidly. It's a healthy corrective to overly optimistic quantum advantage claims.
So how do papers like the end-to-end chemical dynamics simulation by Eklund, Tikku, Huggins, Berry, and colleagues fit into this picture?
The paper End-to-End Simulation of Chemical Dynamics on a Quantum Computer by Eklund, Tikku, Sinnott, Huggins, Lowe, Berry, and Casal is actually quite distinct from ground state energy estimation. It targets non-adiabatic chemical dynamics, processes where the Born-Oppenheimer approximation breaks down, like photochemistry, which are genuinely hard for classical computers in ways that DMRG doesn't easily address. They develop a complete quantum algorithm treating nuclei and electrons on equal footing with bounded error and no uncontrolled approximations, achieving sublinear scaling in grid size through an exponentially faster initial state preparation method. Photochemistry of atmospherically important molecules is their near-term target, and the resource estimates are comparable to other quantum chemistry applications. So this carves out a niche where quantum may have a cleaner advantage.
There were also several papers on error correction beyond the basics. The paper by Heinz, Ostrov, Rudinger, and colleagues on simulating QEC beyond Pauli errors caught my eye.
Simulating quantum error correction beyond polystochastic errors is one of the most practically important QEC papers of the month. The field has long known that real hardware has coherent errors and non-Pauli noise, but simulating their effect on QEC has been computationally intractable. Heinz et al. Develop a technique that maps any Markovian circuit-level error model with small enough error rates onto a detector error model, enabling Monte Carlo estimation of logical error rates. Their findings are sobering. Coherent errors can shift fault tolerance thresholds, increase the space-time cost of magic state cultivation, and raise logical error rates by an order of magnitude compared to equivalent stochastic errors. This means current QEC designs optimized against Pauli noise may be significantly more fragile than assumed.
Related to that, there was a paper by Halasky and Koch on obstacles to continuous quantum error correction. That seems like a fundamental limitation.
Yes, obstacles to continuous quantum error correction via parity measurements identifies a fundamental problem with time-continuous QEC in the circuit QED platform. The issue is that continuous parity measurements require 3-body interactions, but in practice, these are approximated by 2-body couplings to a meter. This approximation corrupts the logical information because you can't simultaneously suppress measurement back action on both the logical and error subspaces. They argue this limitation is quite general. The viable alternatives they point to are either native 3-body interaction architectures or erasure-based encodings. It's a good example of a paper that closes off a seemingly attractive direction and redirects the field.
Let's talk about the distributed quantum computing theme, which seemed to run through several papers. The compiler paper by Durand, Wang, and Feld on logical to physical compilation stood out.
Logical to physical compilation for reducing depth in distributed quantum systems addresses a real bottleneck. When you distribute a quantum circuit across multiple processors, you typically decompose logical gates into sequential physical procedures that require entanglement generation, which adds depth and therefore noise. Durand et al. Build a compiler that identifies sequences of SYNOT gates sharing a control or target qubit and reschedules them into parallel groups that can share distributed entanglement resources. The key guarantee is that circuit depth is never increased. You only win or break even. Benchmark results show consistent depth reductions for inherently sequential circuits. It's a practical tool for the NESC-era distributed setting.
And there was a complementary paper by Wu Ranawera, Rajasegara, and colleagues on time-aware circuit partitioning for distributed quantum computing.
Right. Efficient time-aware partitioning of quantum circuits for distributed quantum computing tackles the upstream problem of how to assign logical qubits to physical QPUs in the first place. Static graph partitioning ignores execution dynamics, while meta-heuristics are too slow. Their beam search heuristic incrementally builds qubit assignments across time steps with quadratic scaling in qubits and linear scaling in circuit depth, much faster than meta-heuristics. They demonstrate lower communication costs than static baselines across varying circuit sizes and network topologies. Together with the Durand et al. Compiler, you start to see a coherent toolchain for distributed quantum computing emerging.
There was also a paper on a factor graph framework for distributed quantum optimization by Huang, Lin, Luo, and Louis. How does that fit in?
A scalable distributed quantum optimization framework via factor graph paradigm is more algorithm-focused than hardware-focused. The key insight is that most optimization problems have sparse structure, not every variable interacts with every other, and you can exploit this by cutting the factor graph along natural seams to get loosely coupled subproblems that fit on smaller processors. They coordinate subproblems with shared entanglement so the network executes a globally coherent search, and they prove this preserves Grover-like OSQRT and query complexity up to separator-dependent factors. This is a significant improvement over naive circuit cutting, which incurs exponential classical post-processing overhead. It's structure-aware distributed quantum optimization, which is a more principled approach.
Switching to quantum advantage and optimization, the benchmarking paper by Chandarana, Gomez, Cadavid, Solano, and colleagues on the IBM Heron processor was interesting. Did they actually find quantum advantage?
The paper, The Quest for Quantum Advantage in Combinatorial Optimization, End-to-End Benchmarking of Quantum Solvers versus Multi-Core Classical Solvers, is admirably honest. Their hybrid sequential quantum computing solver matches ground state energy in 14 out of 20 benchmark instances in under 1 second, which is impressive. But CPU solvers, including simulated annealing and memetic tableau search, don't match it at the same runtime, while an enhanced parallel tempering method and the GPU-accelerated ABS-3 solver do reach or surpass it. So the result is nuanced. QAOA-style quantum is competitive with some strong classical solvers, but not all, and the comparison is sensitive to what hardware you allow the classical side. It's a reproducible system-level benchmark, which is valuable for tracking progress.
The RWS QAOA paper by He, Apte, Augustino, and colleagues seemed more optimistic about the path to quantum advantage on max-cut. What's their argument?
Regularized warm-started QAOA and conditions for surpassing classical solvers on the max-cut problem introduces a clever modification. They initialize qubits by minimizing expected energy with a regularizer that penalizes near bit string states, preventing QAOA from stalling. This allows fixed, instance-independent circuit parameters, making it effectively non-variational. On Quantinuum's trapped ion processor, depth 6 RWS QAOA on 96-node 3 regular graphs outperforms Goemans Williamson and Halpern Livnat Zwick. Tensor network simulations on 10,000 node graphs show it surpasses classical heuristics under matched restrictions. Even against unrestricted classical solvers, they project a quantum classical runtime crossover below 0.2 seconds on 3,000 node graphs with fewer than 1.3 million physical qubits. It's a credible roadmap rather than a current demonstration, but the argument is rigorous.
There was a broader question raised by Hangleiter's paper. Has quantum advantage been achieved? What's his conclusion?
Hangleiter argues, yes, quantum computational advantage has been achieved, and he provides a careful philosophical and technical argument for why the 2019 Google result and subsequent experiments constitute genuine advantage despite ongoing classical simulation improvements. The key point is that the relevant question isn't whether classical computers can eventually simulate the specific circuits used, but whether quantum hardware performed a computational task faster than any classical computer could at the time under fair conditions. He also outlines what the next steps should be, moving from sampling-based demonstrations toward advantage on problems with clear practical value. It's a useful perspective piece for the field.
Let me ask about the quantum machine learning papers, because there were quite a few. The Quantum Extreme Learning Machine paper by Dao, Yilmaz, Shehzad, and colleagues on 124-qubit IBM systems was striking.
Breaking concentration barriers for quantum extreme learning on digital quantum processors is one of the most impressive experimental QML papers of the month. They deploy a quantum extreme learning machine on up to 124 qubits with circuits exceeding 5,000 2-qubit gates on IBM quantum hardware. The key technical contribution is identifying a regime of optimality at small scales that transfers to larger systems, combined with a local eigentask analysis for efficient feature selection. They achieve performance competitive with leading classical baselines on time series forecasting and satellite image classification. The concentration barrier problem, where large quantum systems lose input-output distinguishability, is addressed through multi-objective hyperparameter tuning. This is one of the first large-scale pre-fault-tolerant QML demonstrations that holds up against serious classical comparison.
The paper by Bellis, Bowles, Gupta, Peters, and Schuld on spectral methods and quantum ML seem to offer a more conceptual argument for why quantum might help. Can you summarize their thesis?
Their argument in spectral methods, crucial for machine learning, natural for quantum computers, is elegant. They observe that spectral methods, manipulating the Fourier spectrum of a model, are fundamental to classical ML. SVMs regularize in Fourier space, CNNs build Fourier filters, and there's a hypothesis that spectral bias underlies deep learning's success. Quantum computers, they argue, are naturally suited to spectral manipulation because the quantum Fourier transform is a native operation, and quantum states can represent probability distributions whose Fourier spectrum you can directly manipulate using the full quantum toolbox. For classical generative models, this is prohibitively expensive. So the paper is really asking, could quantum computing give us fundamentally more direct control over the spectral properties of ML models? It's a compelling research agenda rather than a result, but it's the kind of principled why quantum argument the field needs.
There was also a paper by Bellis, Crognaletti, Argentin, Grossi, and Schuld on probabilistic modeling over permutations using the quantum Fourier transform over the symmetric group. That seems like a concrete instantiation of the spectral idea.
Exactly. Probabilistic modeling over permutations using quantum computers is a direct application. The symmetric group Fourier transform is classically intractable for large permutation spaces, but quantum computers can do it with a super exponential speedup. They construct a quantum algorithm that encodes an exact probabilistic model over permutations, capturing all interaction complexities via low and high frequency components into quantum amplitudes. Applications include multi-object tracking and recommendation systems. It's an honest paper. They discuss scaling limitations and practical challenges, positioning it as a first step. But it's a concrete use case where the quantum Fourier transform does something classically hard, which is rarer than you'd think in QML.
I want to ask about the AI-driven algorithm discovery paper by Finger, Rapp, Kaladindi, and a large DeepMind adjacent team. Using LLMs to discover quantum algorithms feels like a new direction.
Automated near-term quantum algorithm discovery for molecular ground states uses a platform called the Hive, which drives an evolutionary search using large language models to synthesize quantum programs. They discover heuristic algorithms for LIH, H2O, and F2 ground states with significant reductions in quantum resources compared to state-of-the-art near-term algorithms. Crucially, they also do an interpretability study to understand why the discovered algorithms work. Identifying the key functional components, they benchmark on Quantinuum H2 and identify minimum system requirements for chemical precision. The broader vision using AI to discover quantum algorithms the way AlphaFold discovered protein structures is genuinely exciting, and this paper is an early proof of concept.
On the hardware side, the velocity-enabled neutral atom paper by Lib, Timmer, Amenworth, and colleagues from the Bloch group seemed like a significant architectural innovation.
Velocity-enabled quantum computing with neutral atoms introduces atom velocity as a new control degree of freedom. By exploiting controlled Doppler shifts, they can perform velocity-selective mid-circuit measurements and state preparation on moving atoms without disturbing stationary spectator atoms. They also achieve on-the-fly single-qubit rotations by mapping micron-scale displacements to spatial phases of global beams. Combined with CZ gates at 99.86% fidelity, they demonstrate an 8-qubit cluster state and 242 error detection code and stabilizer measurements with a flying ancilla. The architectural payoff is reduced hardware overhead. You don't need individual addressing beams for every operation, while minimizing shuttling delays. It's a clever way to get more out of the reconfigurability that makes neutral atoms attractive.
There was also a paper on continuous variable quantum computation in superconducting devices by Veloso, Diniz, Solak, and colleagues. CV computing doesn't get as much attention. What's the significance?
Building block for universal continuous variables, computation in superconducting devices addresses a real gap. Superconducting platforms haven't had a scalable architecture for universal CV computation. They design a two-layer architecture using a DC squid as the bosonic mode, a fluxonium qubit for nonlinear interactions, and two ancillary qubits for Gaussian and multimode operations. This implements all 5 gates of the universal CV gate set: rotation, displacement, squeezing, Kerr, and beam splitter, with fidelities above 98% in experimentally accessible parameter regimes. The modular design allows straightforward scaling. CV computing is attractive for certain tasks like Gaussian boson sampling and analog simulation of bosonic systems, so having a credible superconducting implementation pathway matters.
The paper on Kerr parametric oscillators by Kano, Kawakami, Masuda, and a large team from Toshiba caught my attention. KPO-based quantum computers are a less familiar platform.
Change in bit flip times of Kerr parametric oscillators caused by their interactions is an important experimental characterization paper. KPOs are promising for quantum annealing and gate-based computing because they have long bit flip times so the computational basis states are stable. But when you couple KPOs together, photon injection from neighboring oscillators can excite states outside the computational subspace, causing bit flips. The Toshiba team measures this effect directly and finds bit flip times decrease by an order of magnitude depending on injected signal frequency and power. They discuss mitigation strategies including adjusting pump frequencies, coherent state amplitudes, and couplings. This is the kind of careful hardware characterization that's essential for scaling KPO systems.
Let me ask about the quantum error correction infrastructure papers. The GNN accelerator for decoding by Cicero, Altamura, Lange, and colleagues seemed to tackle a very practical bottleneck.
Low latency GNN accelerator for quantum error correction addresses the 1 microsecond decoding deadline imposed by superconducting qubit coherence times. Current state-of-the-art decoders trade accuracy for latency. They implement a graph neural network decoder on an FPGA with hardware-aware optimizations and achieve sub-microsecond latency for code distance up to D7 with lower logical error rates than existing methods. This is a systems engineering achievement. Getting a high-accuracy neural network decoder to run fast enough for real-time QEC is genuinely hard. As surface codes scale up, the decoding bottleneck will only grow, so this kind of work is critical infrastructure.
There was also a paper by Webster, Jacob, and Higgett on distance-finding algorithms for quantum codes and circuits. How does that fit into the QEC landscape?
Distance-finding algorithms for quantum codes and circuits is a comprehensive benchmarking study of methods for computing code distance, which is the key figure of merit for how well a code can detect and correct errors. For quantum LDPC codes, which are increasingly attractive as more resource-efficient alternatives to surface codes, calculating distance is particularly challenging. They benchmark exact methods like Brouwer-Zimmermann and SAT solvers against heuristics like random information set and syndrome decoder algorithms. They further develop the QDistEval algorithm and release everything in an open Python package called code distance. The circuit-level distance calculation is especially important because the detector error matrix of a syndrome extraction circuit is much larger than the code's check matrix. It's a practical contribution that will accelerate LDPC code development.
The paper by Nayak, Beatty, Love, and colleagues on decoding under radiation-induced correlated noise from cosmic rays seemed like a very practical concern for real hardware.
Iterative decoding of stabilizer codes under radiation-induced correlated noise tackles a problem that's often overlooked in theoretical QEC. Cosmic ray muons generate quasi-particles in superconducting chips that cause correlated errors across many qubits simultaneously. Standard decoders assume uncorrelated noise and perform poorly when the actual noise statistics differ from their priors. Nayak et al. Model quasi-particle density as a latent variable and derive an iterative algorithm that alternates between estimating the QP density and decoding under the updated noise model. They demonstrate measurable reductions in logical error probability for surface codes and bivariate bicycle codes. The inferred QP density also provides diagnostic information for device design and shielding. This is the kind of practically grounded QEC work that will matter as systems scale up.
I noticed several papers on quantum classical integration and the broader infrastructure question. The IBM reference architecture paper by Selim, Chow, Corkelis, and many colleagues on quantum-centric supercomputing seemed like a roadmap document.
The paper, Reference Architecture of a Quantum-Centric Supercomputer from the IBM team, lays out a 3-phase vision for integrating QPUs with GPU and CPU infrastructure. Phase 1 treats quantum as a specialized offload engine within existing HPC. Phase 2 enables seamless hybrid quantum classical algorithm execution through advanced middleware. Phase 3 is fully co-designed heterogeneous quantum HPC systems. The motivation is that current workflows force users to manually orchestrate between quantum and classical systems, which is a major productivity bottleneck. The paper is notable for being a serious engineering roadmap rather than a research result. It reflects the maturation of the field toward thinking about quantum as part of a broader computing ecosystem.
The reproducibility paper by Vertiak, Batten, and Torres Knoop raised some interesting methodological concerns about classical quantum integration. What did you make of it?
Rethinking reproducibility in the classical HPC quantum era toward workflow-centered science makes a point that the field needs to hear. Quantum computing amplifies existing reproducibility problems in HPC, hardware dependencies, documentation gaps, probabilistic outputs, hardware-specific noise, while adding new ones through tight software-hardware coupling. Their proposed solution is workflow-centered science, developing meta-workflows that document both process abstractions and implementation contexts. The key insight is that in quantum classical hybrid systems, the infrastructure itself becomes part of the result, so you can't separate the two. It's a methodological paper, but it's practically important as quantum computing moves towards scientific applications where reproducibility is essential.
There were also security-focused papers beyond cryptography. The QSPI paper by Raj and Balachandran on a quantum remote access Trojan was alarming.
QSPI, a quantum rat for circuit spying and IP theft, is a wake-up call for the quantum cloud computing ecosystem. As users submit circuits to cloud backends, they implicitly trust the submission pipeline. QSPI demonstrates a proof-of-concept man-in-the-middle attack where a rogue certificate authority intercepts quantum circuits in transit, forwards them to a remote server for analysis and storage without disrupting execution or triggering authentication failures. The target is IBM Qiskit APIs on Windows, but the attack model generalizes to any delegated quantum workflow. The paper highlights that classical attack primitives, malware, MITM, certificate spoofing, are directly applicable to quantum workloads, and the field has largely ignored submission layer security. This is an important gap to close.
There was a companion paper by the same authors on data obfuscation for protecting classical values during quantum computation. Is that a viable defense?
Data obfuscation for secure use of classical values in quantum computation proposes encoding sensitive classical data into structured quantum representations across multiple registers using reversible quantum operations and amplitude amplification to allow selective recovery without exposing the underlying data. The authors are careful to frame this as a complementary security primitive rather than a complete solution. It protects against a specific threat model where the execution environment is partially untrusted. The resource requirements are non-trivial, and the practical limitations are honestly discussed. It's an early exploration of a genuinely new security problem that will become more important as quantum cloud computing scales.
Let me ask about some of the more foundational or theoretical papers. The paper by Polson, Sokolov, and Zantadesky, Connecting Bell Inequalities to Causal Inference and Bayesian Computation, was quite ambitious.
Bell's inequality, causal bounds, and quantum Bayesian computation, a unified framework, draws a deep structural correspondence between Bell's theorem and causal inference. The key observation is that the local hidden variable polytope in quantum foundations is structurally identical to the marginal compatibility polytope in causal inference. Fine's theorem about CHAH inequalities is precisely the pivot. The instrumental variable model in econometrics is equivalent to the Bell local hidden variable model. They extend this to algorithmic and entropic formulations, the NPA hierarchy, and MIP-RE undecidability. The practical payoff is that quantum Bayesian computation exploits the same non-commutativity that enables Bell violation, yielding polynomial speedups for posterior inference. It's a unifying framework that could open new directions in quantum causal inference algorithms.
The paper by Burkat, Strelchuk, and Studzinski on exchange quantum polynomial time circuits using only the Heisenberg exchange interaction was also theoretically interesting.
The power of swap, post-selected quantum computation with the exchange interaction, introduces XQP circuits, quantum computation using only computational basis, state preparation, and measurement, plus the isotropic Heisenberg exchange interaction. This is sub-universal but sits strictly between BPP and BQP. Efficiently simulating XEQP to multiplicative error would collapse the polynomial hierarchy. Remarkably, even the restricted family using only SQRT swap gates remains hard to simulate. They also show SCART swap gates generate T designs for SU2 invariant unitaries and maximize entangling power within XQP. The connection to 6-vertex and Potts model partition functions is beautiful. The practical relevance is that exchange interactions are naturally available in spin-based hardware like quantum dots, so XQP circuits are a natural target for near-term demonstrations of quantum advantage.
There were several papers on quantum error mitigation as distinct from error correction. The guess technique by Oliva del Moral, Sanz Larate, Fraxinet, and colleagues seemed particularly practical.
Noise mitigation of quantum observables via learning from Hamiltonian symmetry decays introduces guess, guiding extrapolations from symmetry decays. The idea is to exploit Hamiltonian symmetries. You learn extrapolation coefficients from a symmetry observable and use them to estimate target observables. They test on IBM Heron hardware with 100 qubit systems and circuits up to 8,000 CZ gates, achieving around 10% relative error while requiring only twice the shots of baseline Z&E. They also demonstrate statistical post-selection based on symmetry observable outcomes, which provides quality information about target qubits. For utility-scale circuits, this is very practical. It's a low-overhead mitigation technique that leverages physical structure rather than brute force noise amplification.
And the quantum-enhanced Pauli propagation paper by Majumdar, Garrison, Luo, and colleagues from IBM seemed to take a different hybrid approach to mitigation.
Quantum-enhanced Pauli propagation, or QAPP, is conceptually clever. Instead of using classical resources to mitigate a noisy quantum circuit, it uses quantum resources to improve a classical polypath simulation. They use Clifford perturbation theory to construct a classically simulable ensemble, then use noisy quantum expectation values of this ensemble to infer a global rescaling factor that corrects the target circuit execution. The result is provably asymptotically unbiased, requires no noise characterization, and applies to arbitrary circuits. On IBM Heron hardware with 49 qubit random mirror circuits at depth 80 and trotterized Hamiltonian evolution, they show consistent improvements over both classical, CPT, and unmitigated quantum results. It's a model-free scalable framework that bridges classical simulation and quantum execution.
I want to touch on the photonics papers. The gigahertz single photon source paper by Behrens, Rickert, Qubits, and colleagues seemed like a hardware milestone.
Gigahertz clocked generation of highly indistinguishable photons at C-band wavelengths reports single photon generation at 2.5 GHz clock rate in the telecom C-band, which is the wavelength range used for long-distance fiber communication. They achieve multi-photon suppression below 4% and two-photon interference visibility above 85%, close to the theoretical limit. The key enabler is a semiconductor quantum dot in a microcavity with strong asymmetric per-cell enhancement driven by pulse two-photon resonant excitation. For quantum communication networks, having indistinguishable photons at gigahertz rates in the telecom band is essential. This is the kind of hardware advance that makes interference-based quantum networking at real data rates conceivable.
There was also a paper by Boris Vasquez, Eweniuk, and Rotenberg on quantum photonic neural networks encoded in time rather than space. That's a different architectural approach.
Quantum photonic neural networks in time is architecturally elegant. Spatially encoded photonic neural networks require more physical components as you scale up. More phase shifters, more switches. Time-bin encoding uses the same number of photonic elements regardless of network size or depth, which is a major scaling advantage. They model imperfections, including losses, routing errors, and distinguishable photons, train the network to implement a C0 gate, then extend to a realistic two-photon nonlinearity from a quantum dot coupled to a waveguide. The resulting Bell state analyzer achieves 96% fidelity, improvable to 99% with time gating while maintaining over 90% efficiency. It's a credible path to scalable photonic quantum neural networks.
Let me ask about the Hamiltonian certification paper by Flamia, Kitron, Ma, Sakura, Tong, and Zhang. Autonomous calibration monitoring seems very practically important.
Autonomous Hamiltonian certification and change point detection solves a subtle but critical problem. Quantum devices need recalibration as Hamiltonian parameters drift, but the gates you'd use for sophisticated verification might themselves be miscalibrated. Their solution uses only single qubit gates and measurements, making the protocol robust to exactly the miscalibration it's trying to detect. They achieve sample complexity scaling as ON log 1 delta epsilon squared and develop an online change point detection algorithm using the QSUM procedure that matches asymptotically optimal scaling. The key technique is evolving random stabilizer product states and performing adaptive single qubit measurements based on a classically simulable hypothesis state. This enables quantum devices to autonomously monitor their own calibration without ancillary systems or a trusted reference, a practical necessity for reliable operation.
There were several papers touching on quantum advantage in specific application domains beyond chemistry. The Transport Research Review by Oberg, Corey, Kadami, and Basker was interesting. I hadn't thought much about quantum computing for traffic systems.
Quantum Computing for Transport Research, an introduction, systematic review, and perspective is a thorough survey covering 103 studies. Transport engineering has combinatorial optimization problems, routing, signal coordination, traffic flow, that are naturally suited to quantum approaches. They identify a pipeline from problem formulation through quantum algorithm selection to implementation, and they're appropriately cautious. They conclude that future research should prioritize problems where quantum offers a clear practical benefit rather than quantum washing classical problems. The companion paper, Quantum Algorithms for Network Signal Coordination by Dixit and Pesh, actually implements Grover's algorithm for the NP-complete network signal coordination problem, demonstrating quadratic speedup and extending to a robust formulation. It's a nice example of domain-specific quantum algorithm development.
I also noticed the paper by Ansari, Feniu, Gorod, and a large team from Qubit Pharmaceuticals on quantum computing for drug discovery. How realistic is that vision?
The Convergence Frontier, integrating machine learning and high-performance quantum computing for next-generation drug discovery, presents a tripartite vision. ML foundation models like Phoenix Bio 1 for quantum-accurate molecular dynamics, classical HPC for scale, and quantum computing as the ultimate accelerator for generating quantum chemistry training data that classical methods can't produce accurately. They argue that hybrid QPU-GPU architectures using Hilbert space mapping can achieve true chemical accuracy while bypassing classical approximation heuristics. It's an ambitious roadmap paper that positions HPQC as the beyond GPU frontier for drug discovery. The honest assessment is that this is a 5-10-year vision, but the logic is sound. Quantum chemistry data generation is exactly where quantum computers should add value to ML-driven drug discovery pipelines.
Before we wrap up, I want to ask about a few papers that seem to address more foundational or cross-cutting themes. The Uncertainty Quantification Review by Benink, Bukovska, Piper, Ramirez, and Wong seemed like it was trying to bridge two communities.
Uncertainty quantification for quantum computing is a genuine bridge-building effort aimed at mathematicians and computational scientists. It grounds quantum computation in statistical inference, probabilistic modeling, Bayesian inference, sensitivity analysis, and shows how these tools address error propagation and reliability in NISQ devices. The framing is that UQ methodologies can guide validation, error mitigation, and principled algorithm design. What I find valuable is that it narrows the conceptual divide between applied mathematics and quantum information science, which could bring a large community of computational scientists into productive engagement with quantum computing. The field needs more of this kind of interdisciplinary translation.
And the paper by Kasiku and Garcia-Zaparain on causal identification of genuine quantum contributions in QML circuits. That seems to address a persistent confusion in the field.
How quantum circuits actually learn, a causal identification of genuine quantum contributions, uses counterfactual causal mediation analysis to decompose performance differences between quantum circuit architectures into direct effects from parameterization and expressivity versus indirect effects mediated by genuine quantum resources like entanglement entropy and quantum mutual information. Their finding across 43 validated configurations is striking. Direct architectural contributions exceed quantum-mediated effects by a mean ratio of 13.1 to 1, with quantum effects contributing only about 0.82% on average. This means current variational quantum circuits are operating far below their quantum potential. Most of what looks like quantum advantage is actually classical architectural scaling. It's a sobering but important methodological contribution that should inform how the QML community designs and evaluates circuits.
That's a great note to reflect on. Looking across all these papers, what would you say are the 2 or 3 dominant themes of March 2026?
I'd highlight 3. First, the maturation of fault-tolerant quantum computing from theoretical to experimental. The Cain et al. Results on 10,000 qubit Shor's algorithm, the Perlin et al. End-to-end FT algorithm execution, and the STAR architecture papers collectively show that fault-tolerant quantum computation is moving from a distant goal to an engineering challenge with a credible timeline. Second, the honest reckoning with quantum advantage. Papers like the Legeza et al. DMRG benchmark, the Chandarna et al. Optimization comparison, and the Kisiku et al. Causal analysis all push back against premature advantage claims, which is healthy. Third, the emergence of quantum computing as part of a broader ecosystem, distributed quantum computing, quantum-centric supercomputing, quantum security, and quantum software engineering are all maturing into serious engineering disciplines rather than theoretical curiosities. The field is growing up.
That's a really helpful synthesis. The tension between optimism about fault-tolerant timelines and honest benchmarking against classical methods seems like the defining intellectual tension of the moment. Thanks, Bob. This has been a great tour through a very dense month of research.